Well, good evening. It's a great honor for me to be here. The last time I was in the Sheldonian was 26 years ago when I was getting my DPhil with my parents present. So quite nice to be back, and it's really quite an august setting. So what I'd like to do, sort of based on guidance from Simon, was to use the global burden of disease work that is ongoing, the Global Burden of Disease 2013, talk about the analyses that have been done for HIV, tuberculosis, and malaria, but at each step in that also point out the major weaknesses and some of the opportunities that I see as a sort of personal view of ways to improve our ability to track these diseases. For those who aren't familiar with the GBD 2013, a few slides or a few words about the nature of the study. So the last iteration of the Global Burden of Disease that was published in full was the Global Burden of Disease 2010 study. It was published in The Lancet about 2 years ago. And then fortunately, the Bill and Melinda Gates Foundation has funded a now annual process of updating. And this is viewed as essentially a global public good of synthesizing what we know about descriptive epidemiology in a coherent way and making it available for everybody to use. So what exactly are we trying to achieve? And that is what Simon already said, which is a systematic analysis of the loss of health across a broad spectrum of diseases, injuries, and risk factors, to do it by country, 188 countries now, and over time, by year from 1990 to present. It now, because of broad interest generated by the burden of disease in 2010, is including subnational assessments for China by province. In the UK, we've got a collaboration with Public Health England, where we've actually now produced with them analyses for the regions of England and then by deprivation level within regions of England. And we also have a collaboration in Mexico that's yielding assessments at the state level in Mexico. Turns out there's other countries that are going to be contributing to subnational assessments in the future, and in Q&A, if that's of interest, we can explore that. In the current iteration, we now cover 323 diseases and injuries, 1,500 different clinical sequelae of those diseases and injuries, and 72 different risk factors. So really quite broad and comprehensive, and so by the very nature of the undertaking, we need to draw in very broad expertise around the world in these different outcomes and risk factors. And that's really why I'll be talking about the GBD and making use of the GBD 2013 results, but these are not things that I've done. At the Institute for Health Metrics and Evaluation, we're simply the coordinating center for a huge multi-investigator collaboration. We're now more than 1,000 investigators from more than 100 countries that are contributing in different components of the study. So the key thing to sort of put in context for the global burden of disease is it is a body of work that started in 1992 and has evolved over the last 22 years to be increasingly a highly standardized, protocolized approach to integrating multiple data sources to understand the key blocks that go into measurement of burden. And this schematic is a very simplistic one. I'll show you a more detailed one in a moment. And then there's a cascade of ever more detailed schematics that show how each type of data gets used and the types of corrections that are done to those data sources. Top left block is measuring basic demographic rates, age-specific death rates. Top right block is all the steps and data sources that go into trying to measure causes of death. The bottom right here is the attempt to measure disease incidence and prevalence. There's an attempt to figure out comorbidity that's behind the scenes because it matters for figuring out the disability component of the burden of disease, how many combinations of conditions people have. And then the blue boxes is our attempt to measure risk factors. Now, you can ever go into more detail here, and the reason we produce these schematics and try to publish them is that so people can actually try to trace how each type of data gets integrated into the analysis. And there's a progressively elaborated set of largely Bayesian statistical methods now used to do the data synthesis part of these components. Purpose of this lecture is not to do a deep dive on each component. I'll do that for the three diseases in a little bit more detail. Now, why is the GBD useful? And I think one of the main reasons it's a useful undertaking is that it allows for more meaningful comparison across time and place than simply looking at the raw statistics that get produced in different countries. That's because a tremendous amount of effort goes into dealing with what we call garbage coding. So the co-originator of the global burden of disease, Alan Lopez, and I, since the beginning, we've paid a lot of attention to how different systems assign underlying cause of death. There's marked variation across countries. For example, French physicians don't like to talk about ischemic heart disease. They talk about general atherosclerosis on death certificates. So you get the so-called French paradox, which is partly, not entirely, related to coding practice. So there's a lot of work in the burden of disease in trying as best one can to correct for these variation in coding practice. Likewise, for disease prevalence, in the systematic reviews for diabetes, we just find studies that use 19 different definitions of diabetes. And so we try, to the extent you can, to map those different case definitions statistically into what might be the rates in a common case definition. Now, the other thing that the GBD does is uses traditional metrics, disease prevalence, death numbers, death rates, but death probabilities in different periods of the lifespan, but also produces 3 summary metrics to help look at large patterns in the data. One is converting deaths by age into years of life lost, and that's done using a standard reference life table. Simply, you've lost more of your normative lifespan if you die at age 5 than at age 80, and we use one single life table, reference life table, to compute that. For years lived with disability, also equally simple. It's the prevalence of all the conditions in the GBD multiplied by a severity score that's measured from the general public. So it's surveys of the general public, their view about severity, and years lived with disability is just prevalence times severity and summed across conditions. And then the apex measure in this system is DALYs, and that's simply the sum of years of life lost with years lived with disability. Now, GBD 2010, some of you may have seen the papers that were published in The Lancet. The GBD 2013 cycle is what we're in now, and that's updating the numbers from 1990 to 2013. There's some major developments on some of the risk factors and change in methods, some changes for some of the diseases, as we'll talk about in a moment. And so to date, there's been 5 main publications from the GBD 2013, our tobacco analysis in JAMA, separate analyses around obesity, and then the MDG4, 5, and 6 papers that have come out electronically and now in print this last week. There will be similarly summary papers on cause of death, on risk factors and DALYs that are coming, and then many disease and risk factor specific studies that will be released. Okay, so that's some context. So now I'd like to go into a little bit more detail on HIV, AIDS, tuberculosis, and malaria, highlighting some of the key changes and some of the key challenges as we see it. So in the GBD 2010 for HIV/AIDS, we largely used the very extensive modeling effort undertaken by UNAIDS as an input into the GBD 2010 with minimal change, except around cause of death, where we forced the sum of cause-specific mortality to equal the demographic estimates of all-cause mortality. But bar that, no change. For the GBD 2013, we've undertaken a much more fundamental look at the modeling effort around HIV. And I think the way to think about this, there's 2 components in the UNAIDS modeling approach, and we've followed their basic framework. There's the EPP component, which is back estimating incidence from prevalence data. And then there is the progression of incident cases by age and sex to death, taking into account both location and access to ART, PMTCT, and other treatment options like cotrimoxazole prophylaxis. So what we started with is the latter part. We focused our energy in thinking about the HIV epidemic on understanding the progression from incidence on, and we haven't done much on the incidence part in generalized epidemics, but some in concentrated epidemics, as you'll see. Probably the most critical component is we undertook systematic reviews of published cohort studies. to inform some of the key model parameters, and in particular, the on-ART mortality component. All right, a little bit more detail. Big change in the concentrated epidemics was that we believed that, bar 1 or 2 countries where there's actual data on the fraction of the population that belongs to high-risk groups, most of the assessments for high-risk groups are based on expert opinion, and we believed a firmer basis for assessing the magnitude of an epidemic in a concentrated epidemic, that's where it's not in the general population, it's in high-risk groups, was using cause of death data where it's available. In the generalized epidemics, we changed, lowered the survival or raised the death rates based on our systematic review of individuals on ART in many African programs. And then the third and largely unresolved problem is that there's a real mismatch in 4 or 5 countries in Southern Africa between the demographic data on all-cause mortality and the modeling of HIV-related mortality of progressing incidence cases right through to death. Often the number of HIV deaths are multiples of all-cause mortality. And it's really hard for us to figure this out, to put it bluntly. So a step in this process is we took the UNAIDS Spectrum program, we recoded it in an open source language, Python. The main advantage of that is it takes a program that was actually rather an old language, written in the late 1980s, modernized it and allows us to do this much more fast, and we were able therefore to do sort of brute force uncertainty analysis by iterating through the program thousands or tens of thousands of times for each country. So the net effect of this is that 2 very important global reflections of the epidemic. In concentrated epidemics, where we shifted to using, for example, in a country like Brazil or Mexico or in Thailand, using cause of death data, we end up, on average, finding that the epidemic is smaller than the assessments based on expert judgment of the size of high-risk groups. And an important footnote to this calibrating based on cause of death data is that you have to fix some biases in the cause of death data to start with, because there's a tendency in some countries to sign HIV-related deaths to things like meningitis, or in some cases some cancers, or even just generally to pneumonia. And so in a previously published study a few years ago, some investigators at our institute developed a method to try to figure out where HIV deaths were being misassigned based on the temporal dynamics of the age-sex pattern. So if you suddenly saw an increase in the number of meningitis deaths in Thailand from pre-HIV to during the HIV epidemic in 20 to 40-year-olds, we assumed that that increase was due to HIV, or misassigned HIV. We reassign those deaths, and here's what happens, for example, in Thailand, where the directly coded HIV deaths are in red, and then these reassignments are in blue and green using different algorithms. In some places like Russia, the vast majority of HIV deaths appear to be misassigned, and therefore this reassignment algorithm matters quite a lot for increasing the number of deaths as estimated in vital registration. Okay, so here's an example of what we've done in changing the concentrated epidemic. The orange lines here are the epidemic curves of estimated death numbers for Panama based on the original UNAIDS assumptions of the fraction of the Panamanian population in different high-risk groups: intravenous drug users, men who have sex with men, and female sex workers. The gray dots here are the actual number of deaths recorded nationally in a reasonable vital registration system in Panama due to HIV after these corrections for miscoding. And so there's obviously a huge mismatch between these in a place like Panama. And what we've done is we've recalibrated these epidemic curves from Spectrum to say what would incidence have to have been to observe these numbers of deaths. And those are the orange lines. It's not a perfect match, I think there's a lot of improvement, as I'll mention in a moment, that one can do in the future to improve this sort of modeling. But the basic construct here is that using a nationally representative data system, like good cause of death data, or reasonably good, is probably a more robust way to track HIV than trying to use expert judgment about the fraction of the population in these high-risk groups. Now, the effect of that, by the way, is to raise the magnitude of the epidemic in some countries, the Philippines, Guyana. We end up with larger epidemics, Belize, than had previously been estimated. But globally, on average, it's to reduce by half or more the size of the concentrated epidemics. Now, the main effect for the generalized epidemics, where most of the harm from HIV clearly lies, has been to modify the death rates, raise them for individuals based on receiving ART in low-income country programs. What we saw in the systematic review of published cohort studies was huge variation in observed death rates of individuals on ART, some with very low death rates akin to high-income countries, and some of those quite well-known programs in Africa, but the average was quite a bit higher. And so, to put it another way, the benefits of ART are not being fully realized because of issues around what we think of as quality. And that's both retention, but could also be issues around the quality of programs of those that still remain in treatment. Now, at the end of the day, the results from our analysis compared to the one source that we can probably hang our hats on for generalized epidemics, which is population-based serosurveys, are shown here. The blue dots are the GBD analysis that's published, and the red dots are UNAIDS analysis. The x-axis is the prevalence by age, sex group in nationally representative surveys in 43 countries, and the y-axis is the estimates. As it turns out, if you just run a simple fit statistics, there's a slightly better fit for the GBD compared to the surveys than for the UNAIDS numbers, which are about 7% on average higher than the surveys. But that's a pretty small difference given all the uncertainty that's in the sort of modeling in the background. But either way, this alternative, taking into account lower death or higher death rates, lower survival on ART, still fits the prevalence data. So what does this mean at the global level? It means that our prevalence estimates, because we also have in the modeling these lower numbers in the concentrated epidemics, but we also have longer survival in some parts of Africa, particularly Eastern and Southern Africa, pre-ART. All of that combines to say that total prevalence is somewhat lower, but still rising in the GBD assessment shown in red as compared to the UNAIDS assessment shown in blue. Same here for death, but a little bit more marked difference, where the decline from the peak of HIV around about 2004 to 2005 is attenuated because of this higher death rates on ART. Now, the counterfactual number of deaths in our modeling, if you took away ART, continues to rise more steeply. So the benefits of ART remain very large quantitatively. It's just that they are smaller than perhaps we thought before. Here's a map of, no surprise here, where HIV mortality here measured as the crude death rate per 100,000 is concentrated. And I think this largely, geographically fits quite well what previous assessments have shown as well. Now, one thing that you can do in the modeling is to run a counterfactual assessment where we said what would have happened to HIV mortality if you did not have ART and you did not have PMTCT, prevention of mother-to-child transmission. And the answer is that a huge number of extra years of life have already been added. So during the period in just the last 5 years, 2009 through 13, there's been almost 14 million extra years of life lived because of those interventions. So that's a pretty large benefit, and we're not counting in this assessment years that will be lived in the future because of prevention of infection due to PMTCT. Obviously, the ART benefits are coincident with the year of ART, but for PMTCT, you prevent a child being infected, there's a stream of health benefits that will continue into the future. So this is a very conservative view of the actual additional years that have been lived due to interventions. Now, an interesting exercise here is to relate spend, here only the spend by the donors. So this is development assistance for health for HIV/AIDS, accumulated over the period 2000 to 2011, divided by how many extra years have been lived. And this is essentially a expenditure per year lived. It's very low in a place like Brazil because most of the money being spent there is their own money, which is not being counted in the numerator. But in Africa, where much of the funding, but certainly not all, is coming from development assistance for health, you find numbers that are actually pretty attractive, ranging from $3,000 or $4,000 per year of life lived to somewhere around $10,000 per year of life lived. There are some extreme outliers, somewhere around about $1 million per year of life added in Afghanistan. And you can trace some of the history of some of the programs and understand why that might be. If we step back from this analysis, which is an attempt to do a reasonable job with pretty patchy data, there's some pretty glaring observations, which is why, after investing so much money in HIV programs, do we not know much, country by country, about the results of treatment. So the TB world in the 1990s standardized the registration of DOTS, and with some holes, collects globally through the work of WHO almost complete information on the cohort of patients treated with quantification of treatment results at 6 months. Now, you could argue that it's much easier to track the results of TB treatment because it's only 6 months. And for HIV on ART, it's lifelong. Nevertheless, there is no, either in UNAIDS or in our assessment, country-specific information on ART outcome that's being used. We are depending on a systematic review of published cohorts. There's all sorts of publication bias. I would suspect the publication bias is actually towards better outcomes, not worse. And so this is just an enormous hole in our knowledge around HIV, and it's sort of hard to understand why there hasn't been more push globally to try to standardize the cohort registration of data. And I think there's increasing interest in pushing in that direction. But it certainly comes through in a very glaring way. Another example, I think, is the publication of actual incidence studies. These are expensive. Here's SHIMS, the Swazi cohort study that many of you who might follow the HIV literature will be familiar with. Here's a comparison of the reported incidence in the SHIMS study in Swaziland for men on the left and women on the right, and the modeled numbers from the exercise. And it looks pretty reasonable for men, but it looks like our estimates of incidence, remember that's derived mostly from the EPP model going backwards, which we haven't really revised very much yet in the GBD effort, are really quite low compared to what SHIMS is finding. So even though these studies are expensive, I think more studies of actual incidence, and these are not the detuned assay type studies, these are actual cohort active surveillance type studies of incidence, would be informative for calibrating models periodically. The last one is the one that I think nobody really has a great answer for, which is this pretty big disconnect between all-cause mortality analysis, whether that's through sibling history surveys or vital registration data with correction in South Africa, and the modeling from prevalence back to incidence and then incidence forward to death that I've been talking about. This mismatch is up to 20% in some countries, and that's a lot of deaths, and that's a lot of degree of uncertainty. There were some efforts in the GBD process to try to take the two uncertainty distributions from the uncertainty in the demographic estimate and the uncertainty in the modeled HIV and pick the subset that were more consistent with each other, but that doesn't solve the fundamental problem in some countries. It attenuates it, but there still is this problem. And there isn't clarity whether prevalence is overestimated, because if you look at the response rates in surveys, they're around about 60 to 70% these days. Is it that the demographic methods are underestimating mortality, or we're simply over or underestimating survival in the modeling? Last on this is, I think there's some interesting innovations from different groups, both in the UK at Imperial and Josh Solomon at Harvard University, of a new generation of Bayesian estimation methods that would simultaneously use incidence, prevalence, and cause of death data, rather than in this sort of complete separation of the modeling of prevalence to incidence and then from incidence to death. And I think in a year or two, those will come online and be very useful. Okay. So moving on to the second component of MDG6, and that's tuberculosis. This is a disease I used to work on when I was finished here at Oxford and when I was at Harvard. This was the first disease I studied, and it's sort of, although there's some progress in our understanding of the epidemiology of TB, the basic challenges that were there 20 years ago remain, as you will see as I go through this. So the goal, of course, is to use all the available information that exists on TB to come up with our best unbiased, coherent estimate with reasonable uncertainty for incidence, prevalence, and death for tuberculosis. And the way we do that is look at what's out there. So there's annual case notifications. There's expert judgment, which I'll come back to on the case detection rate. There are now more and more population-based prevalence surveys, but still very patchy. And there's vital registration and verbal autopsy data for tuberculosis, which is probably not too bad. And the way we try to analyze this is in a Bayesian meta-regression environment called DISMOD Meta-Regression 2.0, which is a sort of generic tool that's been developed for the GBD. So issues around case notifications. Well, it turns out that what sounds like a simple issue, which is getting case notifications collected at clinics, registered, and I was praising the efforts by the TB community to standardize this just a moment ago. Well, the more you dig deeper, the more there's a few holes there, which is the quality of the data for the subset of pulmonary tuberculosis that is, quote, sputum smear positive. That is, when you take sputum and look at it and stain for acid-fast bacilli and you detect it in a standardized way, the quality of that data for smear positive tuberculosis is actually pretty good and is for almost all countries now reported by age and by sex. The problem comes when we start to look at the other large volume of TB cases, the majority, which are culture positive but smear negative, pulmonary TB and extrapulmonary TB. There's marked variation across countries. So even countries that really we wouldn't expect biologically for the disease to be fundamentally different, in the UK, there's a much higher fraction reported of extrapulmonary TB than, let's say, in France. And in fact, the UK stands out. And it's hard to imagine it's wildly wrong in the UK, but then that means that we would be implying that either there's a different process in terms of the disease progression in the UK, or there's lower quality diagnostics in many parts of the high-income world. Open debate in the TB world. There's also marked tendency, if you dig into the data, to find that some of these other categories are reporting TB suspects and not actual TB cases. There's a lot of X-ray diagnosis still in Asia, and this really muddies the waters a bit as we try to construct time trends. And I'd have to say that we've tried hard with some missing data type algorithms to deal with these problems, but this is, I'd frame this as work in progress. The big problem is the continued dependence in TB epidemiology to estimate true incidence on this unknown number, which is if you take case notifications and divide by true incidence, that's the case detection rate. We don't know true incidence because the number of population-based active surveillance cohort studies are, you can count them on your fingers. So that's not really used. And nobody has a way to get at this unknown quantity, the case detection rate. So currently what's done, and what we've done, we've piggybacked on what WHO does, is essentially national discussions of expert guesses on the case detection rate. This is a very imperfect way to be tracking a major disease, because you are asking, quote, experts to know something they fundamentally can't know, which is true population incidence. And so it is caught in this sort of quagmire of circularity. We really can't validate these expert judgments. The best we can do in the environment that we're modeling TB now for the GBD is to compare it to cause of death data and to compare it to prevalence survey data where available, and to take into account the known relationship of the hazard of mortality or case fatality rate as a function of age and access to treatment, as well as the remission rate also being a function of age and access to treatment. So just a little word about the TB mortality. This is the high point of the analysis for TB, I think. I think there's a lot of vital registration data in the places where TB is still quite substantial. So for example, China now, there's increasingly extensive cause of death data, and China is a source of substantial TB death. The verbal autopsy in places like India, where the Million Death Study and other verbal autopsy studies give us a reasonable fix, and validation studies on verbal autopsy suggest that maybe it's pretty decent for TB, although there's some tendency to misdiagnose COPD or lung cancer with TB, and there's always some concerns about that. But compared to many other causes, TB is pretty decent on the verbal autopsy front. So the cause of death material, I believe, is reasonable. And so what we then do is try to put all this together. And here's the best way to see this is this illustration for Kenya in the year 2013. We have some prevalence data. We have the incidence data. We have estimates of the remission rate. So those aren't measured in Kenya. Those are coming from a global assessment or review of all the data on remission, and that's why the uncertain intervals are very wide. And the same for the excess mortality rate. And then we have verbal autopsy-based estimates of cause of death. And the blue line is the internally consistent estimate of all the parameters at once in this Bayesian meta-regression environment. And that's what we've used for estimating the epidemic. Now, after all that work, the bottom line for TB is actually somewhat of a interesting story, because it suggests that here shown in death numbers, whether you're looking at TB deaths in HIV negatives or TB deaths including HIV positives, the red line versus the blue line, that there's a trend downwards. If you look at death rates, that trend is even more marked. And if you look at the distribution by age, you find what people have known, at least for the last 40 or 50 years, that increasingly TB is disproportionately in males. And the blue bars here, male TB versus female TB in the red bars, there is this interesting hump for younger women where the differential is smaller for reasons that we know that progression to TB in younger women, perhaps related to pregnancy or other factors, tends to be higher. But outside of that range, it's almost 2 to 1 men for women. Now, the main finding, I think, in this analysis of policy relevance is that it appears prevalence and mortality are now declining at faster rates post-2000 than before, which is good news for if you're trying to find crudely some relationship between global fund investments and accelerated progress. This is certainly not proof that global fund investments are the cause of this, but if we didn't see acceleration, it would have been much more concerning. What you do find is, as expected, death rates are going down faster than prevalence, and then the thing that's going down the slowest is incidence. So 0.7% per year decline in incidence, 1.4 for prevalence, and about 3.7% for mortality. But, pretty big uncertainty intervals in these assessments. Compelling story that there is accelerated progress and consistent with, I think, most people's view in the field that we're doing a better job of lowering mortality than we are of lowering incidence. How can we make the TB modeling better? Well, We won't, I believe, have large-scale cohort studies to get true incidence numbers. I think TB is a rare enough disease that that's just infeasible. So I don't think hoping for that as the solution is very likely. I think where we may make progress is a more empirical understanding in different settings of the relationship between excess mortality and remission rates by age, and where feasible to try to trace from prevalence surveys information about whether individuals were treated. Because if you think about it very crudely, the mystery of incidence is, in places where we know prevalence, is we don't really know duration. The literature on duration for TB spans from less than 6 months in a high-income country to possibly, if you believe some of the older studies, more than 5 years in Southeast Asia. So if there's really a 10-fold variation in duration, that means when you have a prevalence survey and no other information, you don't know much about incidence except within an order of magnitude. Now, I think that's extreme, and there's probably ways that one could investigate to try to find in some settings where there are treatment records to try to link the prevalence survey data to what's happened to them in treatment. The other big factor here on TB is that global TB is TB in India. India accounts for an extraordinary fraction of cases and deaths. The analysis that we've done is at the national level. This is too aggregate to be serious, and it's a very high emphasis for the ongoing work of the burden of disease to try to get down to the state or even more local level to build on both case notification data, these sort of expert judgments locally, as well as patchier prevalence data and verbal autopsy data. All right, now on to malaria, probably the weakest area for the estimation of burden across these three diseases. The goal is the same, of course, which is to try to come up with a reasonable estimate of incidence, prevalence, and death from malaria using what data exists. And the data that's out there are in places with very little malaria. There's a lot of vital registration, so that's not hugely helpful, except in a small number of countries with very low burden. Verbal autopsy data, I'll come to that and the issues there, and then getting the incidence from a variety of published incidence studies. So, the big problem with malaria is the use of verbal autopsy data to measure mortality in the places where there's a lot of malaria. And unfortunately, it's the only thing available. Every attempt to measure malaria mortality at some point in the process is using verbal autopsy data. And whether it's buried deep in the modeling or more explicit, and there's lots of issues on verbal autopsy. So in the GBD 2010 analysis, there was a lot of critique, as I'm sure some of you in the malaria community are very well aware, of the sensitivity and specificity of verbal autopsy for malaria deaths, particularly in adults. So one of our research fellows at the Institute spent the better part of a year doing a systematic review of, or trying to find all the validation studies that have been done on VA, and then trying to meta-analyze those. So for children, the verbal autopsy sensitivity and specificity of the studies shown here was low sensitivity, 55%, and for cause of death, very low specificity, 87%. So just think about specificity here for cause of death. If you have specificity of 0.9, that means in the absence of any malaria, we're going to say 10% of deaths are from malaria. That's a big chunk of mortality. So you really need, for cause of death purposes, very high specificity. So it's not like doing individual diagnosis here. On the cause of death level, specificity of 0.87 is really low. Now for adults, sensitivity in the available studies is even lower than for children. Quite a surprise for us. We thought we would find the opposite, that sensitivity was high and specificity would be very low. But it was the reverse. For adults, sensitivity is lower than for children and specificity is higher than for children in the available published studies. Now, the available published studies are pretty weak, but this is it. This is what we know about the validity of verbal autopsy. So if we were to pursue this, we intended originally to take the results and then correct the data for sensitivity and specificity, and believe that that would get at this debate about verbal autopsy overestimating adult death from malaria. When we did the correction, it has the opposite effect, as you can think through in most settings, because of the low sensitivity and the comparatively high specificity for adults. So we didn't think that was a wise idea to implement that correction. We published the results in the Lancet issue that you have on the chair, but chose not to implement that because it would actually increase the number of adult deaths. Based on recommendations of a WHO committee chaired by Peter Smith, we actually also made one other change, which was to not redistribute any garbage-coded deaths, like fever of unknown origin in adults, onto malaria. So we said, already there's enough debate about the number of deaths going to malaria, so we weren't going to add to that by adding deaths from senility or fever of unknown origin being reassigned to malaria. So the net effect of all that was, and actually here's just one thing to point out on the models for malaria. In each of the cause of death models in the GBD, we we hold out some of the data, so we do cross-validation, or however you want to call it, out-of-sample predictive validity, but basically we hold out 30% of the data and then test how well the cause of death models perform in the data that is held out. And I just draw your attention to the fact that the models for adults perform worse than for children in Africa, and the reverse outside of Africa. The models for children outside of Africa are particularly poor performance, and that the coverage of the uncertainty intervals of the data held out is too high. So this is the coverage of the uncertainty interval, which should be 95% for a 95% interval. It's higher than 99%. So basically, what this is telling us is that for a variety of reasons, largely quality of data and poor models, the uncertainty that we generate is too large for malaria. And if you look at the uncertainty intervals by country, they're absolutely enormous. Now, for cases for malaria, we take 87 published studies on incidence that met certain quality criteria, and then we look at the relationship between incidence, PFPR, Plasmodium falciparum parasite rate, and the estimated mortality rate, age, sex, location, and generate a model to estimate incidence. Here's our global incidence numbers. Blue is the WHO estimates of incidence, and red is the GBD estimates. Here's a case where, although the modeling strategies are completely different, they are quite similar. I'm not sure that makes both of them right, but it certainly makes it less controversy about explaining this to different consumers. On death, however, we have higher death numbers, both in children and in adults than WHO, although the gap on adults is smaller now because of the shift of not reallocating fever of unknown origin, particularly in Africa, onto malaria. The other thing to note is that the declines here, as predicted from these very uncertain models, are somewhat larger than the models used by WHO. And the variables in the model that are predicting this decline are both ITN coverage, but also access to ACT. And so that's the other, I think, interesting thing here, and a word on that in a moment. Here's the number of malaria deaths by age. So, of course, as you would guess, there's a huge predominance of malaria deaths under age 5 on the far left, and then malaria deaths across the age spectrum, with a slight predominance of female deaths at the older ages. And whether that's, I mean, it's in the data, it's in the verbal autopsy data, but whether that's real, I think, deserves further exploration. Malaria incidence by country, and you can see the malaria corridor, as you would expect, across from Mali and Mauritania right through to Mozambique, and then pockets of Asia. All right, so what to do about malaria? I think that there is a potential to improve verbal autopsy for malaria. And I think that the lessons we've seen from some of the verbal autopsy research about developing automated methods for verbal autopsy suggests that if you collect a large enough and robust enough validation data set in different locations, you can probably develop automated methods that would do quite a bit better for malaria. And I don't think we've really had the effort that's required, particularly around establishing the diagnostic standards for what is a true cause of, let's say, adult malaria death. And if one could establish those and everybody agreed on them and then go collect this type of validation data, I believe you could develop, as we've seen whenever that is done, improved verbal autopsy methods of the automated nature. Another one that I think we're increasingly interested in is why in the ICD rules, the International Classification of Diseases and Injury rules, do we essentially give precedence to other conditions over malaria? So, example, if you look back in the older literature, you would say there's a relationship between malaria and sepsis. There was relationships that have been established in some older studies between malaria and pneumonia, where it may well be that malaria is the underlying cause, and it's the intermediate cause that's pneumonia, or in some other literature, for example, chronic kidney disease. So following that along, if you look at the well-known ITN trials, the reduction in malaria-specific mortality only explained about half the reduction in child mortality. So put another way, half of the reduction in child mortality due to bed nets was not assigned in the VA in those studies where they had that to malaria. So why shouldn't we compute the total burden or death related to malaria? And in many ways, I think that would solve part of our issue, because we wouldn't actually need verbal autopsy. We could treat malaria as a risk factor, and we then avoid this whole controversy around how well you can assign post hoc cause of death to malaria. Just a reminder of the George G. Glioli study that I think some of you may remember from the Bulletin of WHO in the early 70s, where here's a place in Guyana with abrupt intermission of malaria transmission post-World War II with DDT scale-up, and then in different phases, huge declines in adult malaria deaths as recorded in Guyana, but also associated temporally huge declines in chronic nephritis, acute respiratory disease, and even chronic respiratory disease. So intriguing. There are not many of these natural experiments with data. This happened because in the sugarcane plantations, they had actually very good vital registration. We don't know the quality of the cause of death data, but we certainly know that all vital events seem to have been registered. So, intriguing story from the past. How can we pursue this? Well, I think there's two strategies. There are the sort of ecological studies that I know some groups have been investigating. What's the relationship in cross-sectional or time series cross-sectional models between, let's say, PFPR and some mortality outcome, and you try statistically to control for lots of other determinants? One strategy. I think there will always be doubt about that. And the other strategy would be to literally try to treat presence of parasites at certain quantitative levels, and you could define it differently, and use that as an exposure and do classic epidemiology to look at either odds ratios or relative risks, depending on the study design. I think there's ways to do that relatively quickly given existing data, and that might be an alternative to get out of this sort of conundrum about malaria. What about PFPR? What about the argument that says the world's collecting lots and lots of data on PFPR? We have two very distinguished groups in the world trying to synthesize the data on PFPR. And why don't we just skip the business of estimating mortality and morbidity from malaria and just track PFPR? And that might be the right programmatic strategy. I think, nevertheless, there will be a demand from funders and policymakers for information about or estimates of impact. And so even if the focus of malaria, at least not eradication, but control, is on tracking PFPR over time, then we still will have to come up with some plausible way to go from PFPR and change into death numbers. And the problem there is that the studies that do that go back to verbal autopsy, because these are places where there's lots of malaria, there's no vital registration, there's no medical certification of cause of death. And so that modeling strategy is also dependent on verbal autopsy, and so you get back to the problem that we were just discussing. There's also the curiosity on PFPR of, what's happening? To put it simply, because the publication of Noor's paper with colleagues and Bob Snow in The Lancet this year, where on the left panel you're seeing PFPR around about 2000, and on the y-axis, around 2010, you see a number of countries where PFPR dropped. The right panel is something that I've done, which is take the change in PFPR as assessed by Noor et al. And compare it to the change in ITN coverage. And there's where we start to get concerned, because there are some countries like Nigeria or Mozambique or Sierra Leone where higher ITN coverage is associated with greater reduction in PFPR. But there's places like Malawi that had a 50% coverage of ITN scale up and an increase in PFPR, and then lots of countries on the zero line. So there's a disconnect between the ITN coverage information and the actual estimated change in PFPR. I'm sure we can have a rich debate about is that an issue on the geospatial modeling of PFPR, or is it an issue about who's getting the bed nets? The reason this matters is one of the other modeling strategies, for example, used by WHO, is to have a natural history progression model that goes directly from ITN coverage into reductions in deaths. So if PFPR is actually going up and not down, it's hard to imagine that the simple modeling from ITN coverage to death numbers is going to be robust or reliable. Okay, so let me round out this presentation with just 3 slides. First, general reflection. Bizarrely, given how much the world has invested in the scale-up of funds and intervention for these 3 high-profile, high-impact diseases, there are really large gaps in our knowledge. And those gaps are actually larger for these diseases than for many other conditions. Strangely, I'd say we are better able to track some of the non-communicable diseases, partly because they're more predictable, than we are for some of these diseases. And that these gaps mean that we have truly enormous uncertainty intervals, if you look carefully, for all 3 of these conditions. A couple of things about where we, in the short run, can make progress in the GBD. It's an annual process. Next year, in the 2014 cycle, I think the major change, which will force us to take some position about some of the 3 diseases, is the release of scenario-based forecasts for every country. And that's a large undertaking that I think has lots of potential interesting questions that it'll raise. The other issue is the critique of the risk factor analysis, that we have not included social determinants in the risk factors, and that relates to our rules of evidence. And there's an active discussion about perhaps having a different set of rules of evidence for looking at these distal social factors and keeping that analysis separate from the behavioral, metabolic, and environmental risk factors. Third is the strategy where, again, funding from the Bill and Melinda Gates Foundation, we are progressively trying to add where money goes by the same disease and injury categories as are in the GBD. I think the other general strategy for the GBD, now looking 5 years out, is to try to progress to the point where no unit of analysis is bigger than 1 million people. And that means breaking down, or even more finer grain, but the finer grain the analysis, I think, in fact, although there are small number issues to deal with, tends to lead to better assessments, because there's more direct ways to use local information and knowledge to feed into the assessments. You also detect data errors that are masked at the aggregate level quite a bit more often. And so I think that's a true direction that we see as improving the quality of the assessments. Now, my last slide is to say that some of what I've been showing you, everything I've shown you, is available in online data visualizations if you just go to healthdata.org. And I just want to show you as the last thing that we developed a data visualization for the MDGs. So if you go to healthdata.org, you can find this MDG visualization, which starts with this window which shows you for MDG 4, 5, and 6 the rates of change. So here's Mozambique. It has, from 90 to 2013, a 4% decline in child mortality, a 2% decline in maternal mortality, an increase in HIV, as you would guess, over that time interval, a decrease in TB, and a small decrease in malaria. If you switch to looking at the peak, so you deal with the fact that HIV went up and then down, you get a different assessment, and you can trace how different countries are doing across these different indicators. You can also look at a country view. So here's Uganda, and you can see child mortality, maternal mortality, HIV, malaria, TB, the numbers in any time period, and the ranking based on rates of change for HIV, malaria, TB, maternal, and child across countries. And finally, you can compare any for teaching or other purposes. You can pick any countries you want to make comparisons. So just if you want more information, part of the GBD enterprise is to try to make a wide array of data visualizations available to the public, both for sort of exploring information and for teaching, which I think we already see a huge amount of use, at least in the US, in educational programs of these data visualizations. So thank you very much for your attention late at night.